Hello students, welcome back to my channel. Today we'll be discussing all the aspects related to polarization of light. By all the aspects I mean it will be useful for your class 12th board, JEE mains plus advanced and also in NEET. Regardless of the type of exam, if you know all these things which I'm about to teach, most probably you will be able to handle any kind of question. So without wasting time, let us continue this. Okay. Now, first of all, we have to understand what is polarization of light. But before we understand polarization of light, let us try to understand this simple experiment. Okay. So what is the experiment, students? I'll teach. Now, suppose you have two slots. Okay. One slot like this, later I'll tell you what to do. So this let us say a cardboard or a wooden board, anything is okay. Okay, and this is a vertical notch. Okay, a gap, a slit like structure. Now what we are going to do, we are going to pass a string here. Pass a string. Let us fix one end of the string here, and let us say the other string is being handled by a person. Okay, the other string is being handled by a person. The person is giving an up and down jerk to the what string. So the most probably the string will start vibrating. The string particles will start vibrating, and you can see that these vibrations will be emerging through this notch, that is vertical slot, and they'll be reaching this fixed point. Now imagine, student, that the person is shaking the string, okay, perpendicular to the length. See, perpendicular to the length in all possible directions. That is, he is shaking like this, horizontally inclined everywhere. The string is like this. String is like this, and he is shaking perpendicular to the length of the string in all possible directions. Then, most probably, a three-dimensional kind of a wave will be set up, student. Because the string particles are vibrating in all possible directions perpendicular to the length of the string. So that means it will be just a kind of three-dimensional wave. But if you see to the right side of this notch, this side, then you will find that only those vibrations or those oscillations are allowed to come out of this notch which remain parallel to this notch. That is, only the vertical vibrations are able to come out, whereas rest all the vibrations are absorbed by this plywood or the cardboard, whatever it is. Rest all the vibrations are being absorbed. Only these vibrations which lie in the vertical plane are transmitted. These are transmitted vibrations. Okay. So we say that here this wave was unpolarized wave. The left hand side waves were set up, unpolarized waves were set up. Whereas the right hand side, after emerging through this notch, they have become plane polarized. Plane polarized. Because the oscillations of the string particles are strictly in a single plane. Hence the name plane polarized light, plane polarized wave. So I hope this is clear. Now the most important aspect of this is, you can see here the vibrations which were set up, the waves which were set up on the left hand side here were basically transverse waves. Okay. Why transverse waves? Because the string particles were oscillating at right angles to the direction of propagation of wave. Direction of propagation of wave is along the string, whereas the string particles were vibrating perpendicular to them. So naturally they will be transverse waves. Now in these transverse waves, you can see only those waves were transmitted whose vibrations were parallel to this gap or the notch or the slot. In other words, polarization is taking place only because transverse waves are set up. So polarization is an exclusive property of only transverse waves. Whereas students, we have learned Diffraction is a phenomenon which is common to all kinds of waves, but polarization is possible only in case of transverse waves. Now, longitudinal waves, if you set up longitudinal waves, nothing will happen. For example, instead of vertically up and down or perpendicular to the length, suppose the person generates waves, longitudinal waves, that is along the direction of the wave propagation. So wave will propagate along the length. So let us say that the person is shaking the string along the length is shaking. So these longitudinal oscillations will be set up, students, and this will be able to come out without any problem. Without any problem. In other words, there is no polarization here. Okay, so longitudinal waves cannot be polarized. Cannot be polarized. Okay. Now, examples of longitudinal wave. The most common wave is the sound wave. Okay. Sound waves are all longitudinal waves. Sound waves cannot be polarized. Sound waves cannot be polarized. Okay. So this you have to understand properly. Whereas light waves being electromagnetic waves, all electromagnetic waves are transverse waves. It could be X-rays, gamma rays, ultraviolet, infrared, whatever it is. All the electromagnetic waves being transverse waves, they can be subject to polarization. All can be subjected to polarization. Now I hope what is polarization. So in the process of polarization, the waves attain a single plane. The waves become restricted to a single plane, whereas before polarization, the waves were present in all possible directions, all possible planes. So if this happens with light, and here the oscillations pertain to the electric field oscillation, because we know light wave is an electromagnetic wave. An electromagnetic wave is composed of electric field and magnetic field, wherein we consider only the electric field. In fact, the electric field vector is also known as the light vector. And as a matter of fact, all the phenomena exhibited by light, namely reflection, refraction, dispersion, polarization, everything is mainly due to its electric field, even though magnetic field is also there. So we will always focus on electric field. Unless otherwise specified, we will always concentrate on electric field, even though magnetic field is also present at right angles to electric field. But we may not, we may not be able to discuss about magnetic field right now. So whatever field we are discussing, that is only the electric field of the light, that is electromagnetic waves. So if electric field oscillations get restricted to a single plane, then such light will be known as a plane polarized light. So let us try to understand here, students. Now suppose I have a diagram here. Okay. So that you understand, let me draw this diagram. To save time, I'll be making use of this diagram, students. Okay, because I'm not very good in drawing. Right. So see, you see, light coming from source is unpolarized. So this is the source, students. So light coming from source is always unpolarized, and you can see the electric field vectors shown by the arrows. They are present in all possible directions. Okay. Okay, the directions are shown in a plane perpendicular to the direction of light propagation. You can see light is propagating along this direction, whereas electric fields are oscillating in a plane perpendicular to the direction of propagation in all possible directions. You can see all possible directions. Now, this is a mechanism will understand what is a polarizer. Okay, this is a technique. It is similar to this cardboard which we discussed just now. This is a cardboard with a vertical notch. Quite similar to that, we have a device which is known as polarizer. So when this unpolarized light enters and passes through a polarizer, the polarizer allows only those electric field vibrations which are parallel to its own path axis. Okay, a term which is used, you can also use the term transmission axis. Transmission axis. So any polarizer will have a transmission axis, polaroid. So parallel, only those electric field will emerge which are parallel to the electric field. So automatically this light will now be a plane polarized light. A plane polarized light. So in this chapter, basically we will be studying the different methods of obtaining plane polarized light. The entire chapter revolves around the aspects, different various methods which are employed to obtain plane polarized light from unpolarized light. So as a matter of fact, the light coming directly from any source, okay, directly from any source, it could be a candle, it could be an incandescent bulb, it could be sun, it could be moon, reflected light from sun. All these generate unpolarized light. But if you want to obtain polarized light, you have to make use of certain device. By some special arrangement only you will be able to obtain transmission polarized light. So the entire chapter further discusses what are the different ways to obtain plane polarized light. So next we will be seeing methods of obtaining plane polarized light. Okay. So one by one we'll discuss, students. The first method is by reflection. This is the first method. Altogether we'll be discussing four methods. By reflection, by reflection, by refraction, by double refraction, okay, using Nichols prism, okay, then by dichroism, okay, using Polaroid, and also one more method we'll study is by scattering. Okay, so these are the basic methods which we'll be discussing. I think scattering single R is there. I'm not sure. Yes. So one by one we'll study, students. Let us take the first case by reflection. By reflection. Okay, and also we'll be studying here Brewster's law, because Brewster's law is related to reflection only. Okay. Now suppose this is medium 1 and this is medium 2. Suppose unpolarized light is coming from medium 1. Now unpolarized light, as you know, students, it has electric field components in all possible directions. So this is, I will be showing only in two directions. The reason for this I will explain. Okay. It is enough if we show only in two directions. So electric field vector, this is the incident light. Incident light. Okay, now this is the point of incidence. You have a normal here, normal to the refracting surface. This is the refracting surface. Now there will be a reflected ray as well as refracted ray. Let us say refractive indices are mu1 and mu2 in the two cases. It is found that the refracted ray as well as the reflected ray are partially polarized. So what is the meaning of partially polarized? It means the vibrations in a certain plane have reduced, though not it is altogether eliminated, but the vibrations have definitely reduced in a certain plane. Okay, and it has become more rich in one plane than in other planes. So such light is known as partially polarized light. Partially polarized light. So both the reflected rays as well as the refracted rays are partially polarized. But we want complete polarization. Okay, at least maybe some 98 or 99% polarization we require, though not 100%. Then it is found that we are discussing about reflected light, student. I am discussing only about reflected light. So please focus on this reflected light. So the degree to which polarization occurs in the reflected light depends on the angle of incidence. Depends on the angle of incidence. It is found that for a certain particular value of angle of incidence, the reflected light is almost completely polarized. Okay. Then such that angle of incidence is known as the polarizing angle, sometimes less commonly known as Brewster's angle. So I write it here. Either you can call it as angle of polarization. I think Z will be there in polarization, or less commonly known as Brewster's angle. Then this is the reflected light is almost completely polarized. Almost fully polarized. Okay. So this one method of obtaining. So the corresponding diagram I have, students. I'll just this is the diagram. Okay. So that you understand in a more better manner. So I'll enlarge it so that you understand it properly. See. Okay. Now, Brewster's law states that Brewster's law states that when the reflected light is completely polarized, almost completely polarized. Here you can see it is completely polarized. Okay. Then tan of this polarizing angle I have taken as IP. So I will be taking polarizing angle as IP here. So tan of polarizing angle is equal to refractive index of second medium with respect to first. Okay, that is mu2 by mu1. Okay, refractive index of second medium with respect to first. That is the way we have to write here. Clear, students? So this is Brewster's law. And also we can very well show that if that be the case, then angle between this reflected light and the refracted ray is a right angle. Okay, that is this angle will be 90 degrees. It is easy to show. Why? Let us prove it. If this is IP, then this will also be IP. Okay, right. Now let us find a relation between angle of refraction and IP. Okay. So I will be applying Snell's law here. Okay. Applying Snell's law. Applying Snell's law. We have mu1 into sine of polarizing angle is equal to mu2 into sine of angle of refraction. Okay. Therefore, sine of polarizing angle upon sine of R is equal to mu2 by mu1. But what is mu2 by mu1, students? It is also equal to tan IP. And tan IP can be rewritten as sin IP upon cos IP. Now you can notice, students, that all the angles IP, R, all are acute angles. They are less than 90 degree. So no need to use your brain, trigonometric brain, to find all the possible angles. Only one possibility is there. In one quadrant, most probably in these kind of equations, simple equations, only one possibility is there. So simply cancel sin IP and you can equate the denominators. So sin R will be equal to cos IP. Cos can simply be written as sin 90 degree minus IP. Extracting the sine inverse on both sides, I can write R is equal to 90 degree minus IP, or angle of refraction plus polarizing angle is equal to 90 degree. Now what does it mean? Now suppose we want to know the direction, the angle between reflected ray and refracted ray. Let me see how we can obtain. Now this is the refracting surface, this is the normal, okay, this is the incident ray, this is the reflected ray, and this is the refracted ray. Now this angle is IP because this is IP and this is R. Now if we want to know this angle, for now let us take it as theta. So you can very clearly see that from 180 degree you have to deduct IP and R. Okay, angle contained in a straight line is 180 degree. So I can write theta as 180 degree minus IP plus R. But what is IP plus R? It is 90. So we can write this as 180 degree minus 90 degree, which is equal to 90 degree. So hence it is proved that what? The reflected ray and refracted ray are at right angles to each other. Okay, so Brewster's law states that tan IP is refractive index of second medium with respect to first. This is Brewster's law. And when angle of incidence is equal to the Brewster's angle or the polarizing angle, the reflected light is almost completely polarized. Okay, right. Now regarding these arrows, I'll tell you why it is enough to show only these arrows and dots in case of unpolarized light. Okay, arrows represent those electric fields which lie in this plane, in the plane of incidence, plane of the diagram you can see. Whereas a dot represents those electric field components which are at right angles to the plane of the diagram. Okay, at right angles to the plane of the diagram. So now here we have to understand very important thing. That important thing is this: you have a plane of incidence. See in the diagram, this is the plane of incidence. Is it? This is the plane of incidence. Whereas here the electric field components in the reflected light is perpendicular to the plane of incidence. Did you notice? So that you have to remember, students. Okay, the electric field components in the reflected light is only dots. You can see only the dots. So dot represents electric field which is perpendicular to the plane of incidence. That you have to remember. Okay, then we'll discuss the next type of obtaining plane polarized lights, that is by refraction. So second is by refraction. Now students, you see here, once again let us discuss this. So here you see in this diagram, originally the light was unpolarized and there were equal number of electric field components in the plane of incidence and perpendicular to the plane of incidence. Unpolarized light because electric field components are randomly distributed, but though randomly they are equally distributed in space in all the directions perpendicular to the direction of propagation. So we have equal intensity of electric field components, vector components in the plane of incidence and perpendicular to the plane of incidence. But here what happens in the reflected ray, certain electric field components perpendicular to the plane of incidence have been carried away by this reflected light. So certainly the remaining electric field components which lie perpendicular to the plane of incidence will be present here. Whereas all the electric field components parallel to the plane of incidence will be carried by refracted ray. I hope you got the point. So in the refracted ray, though even though it is partially polarized light, if we can somehow eliminate these dots, if by some method if we can eliminate or minimize these dots, then automatically what will happen? The refracted ray will have only those component of electric fields which are parallel to the plane of incidence. So automatically that will be a almost plane polarized light. So that is a technique used here. So what we do is we allow this unpolarized light. These students, you have a glass plate, okay, any transparent plate for that matter. Let unpolarized light be made incident on this. Unpolarized light will be represented by both the arrows and the dots, okay, and most probably this angle must be polarizing angle, so that the certain dot components of electric field are carried away by the reflected light, whereas the refracted ray, even though more rich in these arrows, it will certainly be having certain dots, okay, not all. Now this is once again made to pass through another transparent slab of the same material, and as you know, if these faces are parallel, then the emergent ray will emerge parallel to the incident direction. So again this angle will be IP. So again the reflected light will carry away certain dot components, and the refracted ray will become more rich in the arrows component, that is the components of electric field parallel to the plane of incidence. Then again it is made to pass through another transparent slab. So same thing, same phenomenon is repeated again and again till the final emergent ray, that is the refracted ray, becomes sufficiently rich in the electric field components which are parallel to the plane of incidence, and most of the dot components are all carried away by reflected rays. So now this ray will be almost fully polarized, almost fully polarized. So this is how we obtain the plane polarized light by refraction. I hope that is clear. Then the third technique is by double refraction. Double refraction. Okay. So here the term double refraction is used in certain cases. It has been found that certain crystals, they exhibit double refraction. What is the meaning of double refraction? A single light ray, okay, a single light ray gets split up into two refracted rays. Two refracted rays. Okay. One is known as the ordinary ray, which in short can be called as the O ray, and the other is known as the extraordinary ray, which can be called as the E ray. Okay. Both are plane polarized light, but their planes of polarization are at right angles to each other. Okay. So this phenomenon is known as double reflection. A single, you can see a single incident light gets splitted up into two different refracted rays. Okay. So I have the diagram. This is the diagram. You can see the diagram, students. Here an unpolarized light is coming. As you can see, it has electric field vectors in all possible directions. Whereas here, as soon as it enters a doubly refracting crystal, this is a doubly refracting crystal. Exhibiting double refraction. So doubly refracting crystal. Okay, example could be tourmaline. Okay, it's a class of boron silicate. Tourmaline is a special kind of crystal which comes under the class of boron silicate. Okay, anyway, So you can see the vibrations which are the electric field vibrations which are in the plane of the this what you call incidence is carried away by the extraordinary ray, and those which are perpendicular to the plane of incidence is carried away by the extraordinary ray, sorry, ordinary ray. So individually both are plane polarized. That is by nature. We don't know how it happens. Of course, there is proper explanation given to this, but it is beyond our scope of discussion here. So that is a law of nature. So therefore, if we are able to eliminate one of the two rays, we will be left with a plane polarized light. Okay, and that is made possible with the help of nickel prism. Okay, that's made possible with the help of nickel prism. So nickel prism is basically a calcite crystal. In brief, I'll explain, students. No need to understand it in details because we'll be learning this in engineering college. So calcite crystal, which is a doubly refracting material, two prisms are taken, two different prisms are taken, and they are properly cut at certain dimensions, at certain angles and all. Okay, these angles and all you learn in engineering college, students. And the two prisms are cemented by a glue, special kind of a glue. I'll explain what is the speciality of this, whose name is given as Canada balsam. Canada balsam, a special type of glue which is transparent, of course. Okay. Now here certain things we have to understand, student. Why one of the ray is known as ordinary ray and the other is known as extraordinary ray? Because the ordinary ray follows Snell's law, and Snell's law states that sin I upon sin R is equal to refractive index of second medium with respect to first. So if this is being followed, that means mu for the material is fixed for this ray. So R is fixed. Whereas the extraordinary ray does not obey Snell's law, which means mu is not fixed for this material. In fact, mu is different in different directions for extraordinary ray. So that is the reason R keeps changing. But there is one or two directions which are known as optic axis, along which the light does not split into two different rays. That is, this double refraction doesn't take place along optics axis. Okay, there could be certain crystals have single optic axis, certain crystals have double optic axis. Whatever be the case, if light is made to pass through the optic axis of that crystal, it will not get splitted up into extraordinary ray and ordinary ray. That is one thing you have to understand. Now, other than optic axis, a single incident ray will always get splitted up into two rays. One of them is ordinary ray and the other is extraordinary ray. As you can see, both carry electric field vibrations in two different directions. Then certainly refractive index will be different for ordinary ray and extraordinary ray because angle of refractions are different. You can see, students, angle of refraction for ordinary ray and extraordinary ray are different. So that means mu of the material will be different. So now the speciality of Canada balsam, as an example I am telling, student. Okay, let us say for ordinary ray, as an example I am telling, these are not actual values. Again I am repeating. Let us say it is 1.48 refractive index for ordinary ray. Then refractive index for extraordinary ray, let us say it is somewhere around 1.52, and Canada balsam refractive index, remember it's not a doubly refracting substance, so it will have a single refractive index. You can see the refractive index of this glue lies somewhere in between the refractive indices corresponding to the ordinary ray and the extraordinary ray. So basically what happens, as soon as an unpolarized light is made incident on a nickel prism, okay, it will get split up into two different light rays. One will be the ordinary ray and the other will be the extraordinary ray. The ordinary ray, you can see it is its refractive index is less than the value of this transparent glue, that is Canada balsam. So it must or it might pass through it without any problem. Whereas for the extraordinary ray, what happens, you see, the refractive index is more than the refractive index of the Canada balsam. So basically light is traveling from denser to rarer medium. So here the angles of the prism are cut in such a way that it undergoes TIR, total internal reflection. So once it undergoes total internal reflection, then the one which is coming out is just a plane polarized light, the ordinary ray here. So this will get a plane polarized light. In other words, if you see the overall effect of a nickel prism, okay, in simple words we can say unpolarized light is made incident on a nickel prism, plane polarized light is obtained. Plane polarized light is obtained. That is the idea behind a nickel prism. So basically we can call it as a polarizer. Okay, we can call it as a polarizer, a device which converts unpolarized light to polarized light. So this is the polarizer. I hope that is clear. So this is how we obtain plane polarized light by double refraction. Okay. Then next is, what was the next, you can see, next is by dichroism. Okay, by dichroism we'll see what is the meaning of dichroism. So next is fourth, by dichroism. So here what happens, this is similar to double refraction but slightly different. Okay. Now there are certain crystals, okay, which absorb the light passing through it to different extents depending on the plane of polarization. Okay, that is when plane polarized light is made to pass through certain types of crystals, different lights are absorbed to different extents depending on the direction of the plane of polarization. So that means what happens is that in certain cases, as soon as unpolarized light enters here, as soon as unpolarized light enters, immediately it splits up into two rays, one which carry the electric field components parallel to the plane of incidence, and the other totally different light ray which carry electric field components perpendicular to the plane of incidence. Now, during the course of motion, as it proceeds, one of them gets absorbed to a greater extent as compared to the other. So this special phenomena is termed as dichroism. So dichroism is a phenomena in which certain crystal absorbs plane polarized light with planes of vibration in a certain direction more predominantly as compared to other plane polarized light. So that means what? If you allow it to proceed, okay, one of the light might get absorbed completely. One of the light, out of the two, one of the light might get absorbed completely, so that we are left with only one type of what you call plane polarized light. So this is the diagram, student. I have the diagram also. I'll bring it and I'll show it here. I'll put it here. So this is the diagram. Okay, you can see that Unpolarized light is incident, you can see students. This is unpolarized light coming, and this is a special type of crystal which exhibits dichroism. As you can see, there are two different plane polarized light within the substance. One has electric field components in the vertical plane as per the figure, and the other has electric field components in the horizontal plane, you can see. The electric field along the horizontal components are being absorbed, okay, during the course of motion. So by the time it emerges, we are left with the plane polarized light is left only with electric field components parallel to the vertical direction, you can see. So this horizontal electric field is completely absorbed. That portion of the polarized light is completely absorbed and releasing or letting out emerge only that component of electric field which is parallel. So this is a plane polarized light. This part. This is a plane polarized light. So this is how we get plane polarized light. Now here you see that this particular plane, you can call it as plane of transmission, or you can call it as axis of transmission, or the pass axis. Sometimes we call it as the pass axis. Now here the thing is that the light might require to move certain appreciable amount of thickness, appreciable amount of distance, before which one of the two plane polarized light is completely absorbed. Okay. So if this thickness is extremely small, suppose we have a special type of material where the thickness is extremely small, then such a device will be simply called as a Polaroid. So what we commonly use the term Polaroid, it is nothing but a special kind of a device which exhibits dichroism, okay, even though the thickness is very, very small. So normally students, you come across books and all, the common type of what you call Polaroids are the H sheet Polaroids. H sheet Polaroids. So now what does it mean? H sheet Polaroids are basically stretched polyvinyl alcohol. Okay, stretched polyvinyl alcohol. It is heated to a certain temperature and is stretched. The polymer molecules, they align themselves in a certain direction, and finally it is cooled and impregnated by some iodine. Then it develops certain kind of pass axis in such a way that is, it allows only that plane polarized light whose electric field components are parallel to the pass axis to emerge through the Polaroid, and the rest is absorbed by it. Okay, so that is the concept of Polaroid. So usually what happens, I'll explain it through a diagram, simple diagram. Here you can take the Polaroid like this. This you can call it as the pass axis through which electric field components are allowed to come. So here you have the electric field components which are both in the plane and perpendicular to the plane. But when it comes out, you have only that plane, that electric field which is parallel to the pass axis. These dot components of electric fields are completely absorbed. Now, a very important thing, students, to solve numerical. If I is the intensity of incident light here, then the emergent light will have an intensity I by 2. That is exactly half of the amount of light is completely absorbed by the Polaroid, and only half is allowed to transmit. This side you have unpolarized light, whereas this side you have polarized light. Now, let me explain you why we show all the components of unpolarized light by these vertical arrows and dots. Is it enough, or is it logical to represent it that way? In spite of the fact that we know that electric field vectors are practically pointing in all possible directions. Now suppose this is a light ray going inside the plane of the figure. So electric field vectors will be oscillating in the vertical direction, horizontal direction, even inclined in this way or in this way. In all possible directions we can see. All possible directions. Okay. Now the mathematical concept is take an x and y axis. Take two axes. The xy plane must be perpendicular to the direction of propagation of light. So light is propagating perpendicular to the plane of the figure. Now you take any amplitude. Let us take A as the amplitude. One of the electric field vector I have taken A as the amplitude. Let us say it makes an angle theta with this. So it will have x component. The electric field will have x component equal to A cos theta, and also it will have a y component which is A sin theta. In other words, all the electric field vectors can be subdivided or can be resolved along x and y component, so that finally you have only two components, that is the summation of all the x components along x-axis, okay, this way, and the summation of all the components along y-axis in this way. So that means we have been able to replace all the electric field components just by two components, one along x-axis and the other along y-axis. So now if you see from this side if you are seeing, then you can clearly see the y components like this, electric field y components like this oscillating, whereas the x component you will see like this. Okay, so this is how we denote. Clear? Right. Now we will be discussing law of Malus. Very important law, students, because in class 12th board exam they usually ask this, and also in different competitive exams. Now what does law of Malus state? I have a diagram for that, so let me pick the diagram. Where is the diagram? Yes, here. Both diagrams are similar, so we can manage just with the help of one. Both are almost similar diagrams. I have picked from some internet sites. Okay, right. So I'll take this diagram. So see, now this unpolarized light, students, you can see this is the unpolarized light. As it passes through one of the Polaroid, okay, then what happens? It is plane polarized light. So you can see this is the path axis. So electric field components parallel to this path axis are able to emerge through this. Okay, so this is playing the role of polarizer. The polarizer. This Polaroid can be called as a polarizer. In fact, in place of polarizer, they can be even nickel prism also, student, because we have already learned that even nickel prism plays the same role. Then you have another polarizer, which here it will be called as the analyzer. Its path axis is tilted, okay, in some different direction other than the path axis of this. That means there is some angle between the path axis of these two. So now only that component of electric field will be able to pass out which is parallel to its path axis. So as you can see, these electric field vibrations are parallel to this plane axis of this. So you have to resolve this direction, and only that component will come. So naturally intensity coming out through this analyzer will reduce as compared to the intensity which is made incident on the polarizer, made incident on the analyzer. So the relationship between this intensity which is observed finally to the intensity which is made incident, that is what is law of Malus. So law of Malus states that suppose you have one of the pass axis like this. Okay, this is the polarizer. Unpolarized light is made incident here. Unpolarized light will be represented by arrows and dots. So the emerging light is a plane polarized light. Plane polarized light. Right? This is the pass axis. Now, this will call it as polarizer. Now what happens? You have another Polaroid and its pass axis is inclined by some angle, let us say theta. Then here only those electric field components will come out which are parallel to the pass axis of this. Okay. So intensity of incident light, if it is like this, I naught here, this is the analyzer. Okay. If I is the intensity, we know I naught is basically I by 2, that we have already learned. So this final emergent light, I'll call it as I dash, will be I naught, that is the intensity of light incident on the analyzer multiplied by cos square theta. This is the law of Malus. Law of Malus. So we can prove this very easily, students. We can quickly see the proof. Now you know intensity varies directly as the square of amplitude. Okay. So viewing in this way, we can see that here the electric field component is E, or let us say E naught, and it is coming in this way, and the pass axis of the analyzer makes an angle theta. So only E naught cos theta component will be able to come out, whereas E naught sin theta component will not be able to come out. Okay. So here the incident light is proportional to E naught square, whereas the transmitted light is proportional to E naught cos theta whole square. Okay. So therefore from here we can write I naught is k times E naught square, and from here we can write I dash is k into E naught square into cos square theta. From equation 1, k into E naught square can be replaced by I naught. So we have I naught cos square theta. This is the law of Malus. I hope that is clear. Right. Okay. Then we are in a position to solve different questions. But before we jump into solving questions, one or two points if I have missed, I would like to recapitulate. I would like to tell you. Okay. So first thing which I would like to tell you is that in plane polarized light, you come across certain terms, that is linearly polarized, then elliptically polarized, then circularly polarized. Okay. Now if you take the plane of vibrations like this, remember light rays passing perpendicular to the plane, then if you have an electric field vibrating along a line, okay, the electric field vibrating along a line, this linearly polarized. light. Now similarly, suppose if you have a what you call a situation in which the electric field vectors are in different directions. For example, at one point of time you have like this electric field, at another point of time it is in this direction, then at another point of time it is in this direction, and another point of time it is in this direction. So if you join the tips of the electric field vectors, they lie on an ellipse. So such a, even though electric field vibrations are vibrating in the same plane, you can see the plane is same, but the direction of electric field is changing and also the magnitude is changing. So the tips lie on an ellipse. So this is elliptically polarized light. Similarly, now you would have understood what is the meaning of circularly polarized light. So circularly polarized light means the electric field vector, the magnitude will remain same, but it will rotate. The tips, when you join the tips of the electric field vectors, they lie on a circle. All are plane polarized light. Okay. So this is a simple plane polarized light which is being obtained through a polarizer. Anything which you obtain through a polarizer is a linearly polarized light. Whereas what happens when you superimpose, okay, two different plane polarized lights? When you superimpose two different plane polarized lights at of different amplitudes and at some phase difference, then usually you get elliptical. Okay, for example, this one possibility I'm just telling you. Suppose you have an electric field along x-axis, linearly polarized electric field along x-axis, and another linearly polarized electric field along y-axis. Okay, their phase difference is exactly pi by 2, let us say, and also they are different in magnitudes. Then you'll get elliptically polarized light. Now here similarly, suppose you have two different linearly polarized light. One is along the x-axis and the other is along the y-axis. Both have equal amplitudes, okay, and their phase difference is exactly 90 degree. Then you will get a what you call circularly polarized light. Okay, so these things are not required. It is beyond the scope of our discussion. Just for your information, I have taught you. Right. Then next we have what is known as specific rotation. Now suppose you have a plane polarized light. Okay. It is made to pass through a aqueous solution, okay, of concentration 10% and length 10 cm. Aqueous solution of that substance, of that substance. Okay. Then if the substance has what you call is exhibits optical isomerism, then one of the isomer will rotate this plane towards right as seen from this side. Towards right means what? Towards right means clockwise, and the other isomer would rotate the plane of vibration here towards left, that is in the anti-clockwise. So accordingly they are respectively named as dextro and levo. Dextro isomers are those which rotate the plane of polarization in the they rotate the plane of vibration in the right hand side, that is clockwise, and levo those which rotate the plane of vibration in the left hand side. So the amount of rotation undergone by the plane of electric field vibrations. This is known as specific rotation. Okay. So this specific rotation is found to be proportional to the concentration of the liquid and also length of the liquid, and is of course inversely proportional to the square of the wavelength. These things have been experimentally found. Okay. So this much should suffice, I guess. This much is enough, and we will quickly discuss different questions, students. Okay. So let us quickly discuss different questions. I'll take you to another page here. Yes. So quickly let us discuss them one by one. So first question is, which types of waves shows the property of polarization? We discussed that only transverse waves show the polarization here. Okay. Infrared is also the answer, but they have collectively asked which types of waves. So transverse waves will be the correct answer. Even microwave could also be the answer, but collectively transverse wave is the answer. Coming to question second, what will be the angle of refraction in the glass if the polarization angle for the air glass interface is this? This is degree, students, 63.8 degrees. So from Brewster's law, we have incident ray, okay, reflected ray and refracted ray. Incident ray and refracted ray, reflected ray and refracted ray are at right angles if angle of incidence is polarizing angle. This we know. Now, polarizing angle is given as how much? 63.8 degree. Okay, we have to find the angle of refraction. Since this will also be 63.8 degrees and we have refraction. Since this is 90 degree, so 63.8 plus R must be equal to 90 degree. So R will be complementary of 63.8, which is how much? Complementary of this is, where is it? 33. So this is 37, 33.7. Is it complementary? 90, this will be how much? Say 60. No, 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 no. Somewhere correct answer is not there, it seems. Correct answer is not there. So I think somewhere there is some mistake, it seems. It should be 26.2. So correct answer must be 26.2 degree. Okay. Some mistake is there, I don't know. Anyway, coming to question 3, what is the polarization angle of a medium of refractive index root 3? So we know that tan of polarizing angle is equal to mu. The other medium is supposed to be air. So whose angle tan is root 3? We know 60 degrees tan is root 3. So polarizing angle is 60 degree. Coming to question 4, which field vector is used to represent the polarization of EM wave? We discussed that only the electric field vector is used to represent the polarization of an EM vector. Sound waves can be polarized. False. We have learned this. Only transverse waves can be polarized. Sound waves are not transverse, so they cannot be polarized. Identify the property which is not mutually perpendicular to the polarized light wave in a plane. Now we have, suppose this is x-axis, this is y-axis, and this is z-axis. Okay. Suppose electric fields are in the xy plane and so this will be known as the plane of vibration. Plane of vibration. Then now the plane which is perpendicular to This plane of vibration will be known as the plane of polarization. There are no electric field components in plane of polarization. There are right angles, which in turn is perpendicular to the direction of propagation. So here you can see direction of propagation is like this. The direction in which light is going. Electric field is oscillating along y-axis and the plane of polarization is along z-axis. So these three are at right angles. So that means the correct answer should be B. Plane of rotation is not related to that. Coming to question 7, in the propagation of light waves, the angle between the plane of vibration and plane of polarization. Just now we learned, students, it is exactly 90 degree. Then coming to question 8, from Brewster's law of polarization, it follows that the angle of polarization depends upon tan of angle of polarization is equal to mu. Okay, and we know from Cauchy's equation, mu is equal to A plus B by lambda square plus C by lambda power 4, which can be omitted, not a problem. So since tan depends on mu and mu depends on lambda, so wavelength of light should be the correct answer. Then a 20 centimeter long tube contains 15% sugar solution, rotates the plane of polarization of light by 21 degrees. Specific rotation of sugar. Now specific rotation will be the angle rotated per 10% solution, this solution. For 15% it is this much. So for 10% it must be this much because it is proportional to the concentration. And also we require for 10 centimeter, not for 20 centimeter. So for 20 centimeter it is this much. So for 10 centimeter it will be this much. So when you cancel this, you will get the answer. Okay. So 3 5s are, 3 7s are, 5 2s are 10. So 70 is the answer. 70 degrees is the answer. Moving to the next question. The critical angle of glass with respect to air is this much. What is the angle of refraction for light incident on glass at polarizing angle? Now, sine of critical angle. See, this is critical angle, students, and sine of critical angle is given as 0.577 is actually 1 by root 3. You should understand this. Okay. Sine of critical angle is 1 by root 3. 0.577 is root 3. Then, which is mu, 1 by mu. So this should be 1 by tan of polarizing angle as per Brewster's law. So that means if tan of polarizing angle is root 3, then polarizing angle must be tan inverse of root 3, that is 60 degree. So C option is the correct answer. Coming to question 11, when a beam of ordinary light is passed through a calcite crystal, the light splits into ordinary ray and extraordinary ray inside the crystal. Both E ray and O ray are polarized, that we have seen at two mutually perpendicular planes, of course. Then polarized light can be produced by nickel prism. We already studied this. Then which of the following phenomena establishes that light, the transverse nature? Transverse nature is established by polarization, because polarization is possible only in case of transverse waves. Then when light from a single point passes through calcite, it often forms two images. Each of the two images are formed from light that has been polarized by. So we saw that calcite is basically a doubly refracting crystal. So that phenomenon is known as double refraction. Okay, each of the refractor rays form its own images. Then coming to question 15, an unpolarized beam is incident at an angle 60 degree on a glass surface, and after reflection it is linearly polarized. That means this angle must be polarizing angle. The approximate refractive index of the glass. We know that tan of polarizing angle is equal to mu. So tan 60 degrees is root 3. Root 3 is 1.732. So C option is the correct answer. If light is allowed to pass through two polaroids P1 and P2 and I naught is the intensity of the polarized light after passing through P1, then the intensity I coming out from P2 will be. This is straight away a question from law of Malus. If light is allowed to pass through two polaroids and I naught is the intensity of polarized light after passing through P1, after passing, then the intensity light coming out from P2. So this is I will be equal to I naught into cos square theta. So I am sorry students, here this 2 should be here. So this is the correct answer. I naught cos square theta. Okay. This is nothing but according to law of Malus. Then nature of electromagnetic waves is transverse. Evidence of this is given by polarization. What happens when sunlight passes through a uniaxial crystal? It gets polarized. Polarization occurs. The phenomena of polarization shows that light has transverse nature. The specific rotation is independent of it is inversely proportional to square of wavelength. The direction in which electric field vectors oscillate in a polarized wave is called the plane of path axis. Okay, path axis. Velocity of light in water is this much. What is the polarizing angle of incidence? Polarizing angle of incidence. Now, tan of polarizing angle is basically mu, and mu is actually CO by Cm. So this is 3 into 10 power 8 meters per second, speed of light in vacuum, upon speed of light in the medium is 3 by 2 into 10 to the power 8 meters per second. So which comes out to be 2. Okay. So we have to find the angle whose tan is 2. Now this is slightly, we have to apply a wise guess, not wild guess, wise guess. Now you see students, tan of 60 degree is root 3. And tan, in the first quadrant, tan is an increasing function. So certainly the angle must be more than 60 because the value of tan is more than 1.73. So the only value which is more than 60 is this. Then next question, two polaroids are kept with their transmission axis inclined at 30 degrees. Unpolarized light of intensity I falls on the first polaroid. Find out the intensity of the light emerging from the second polaroid. So here unpolarized light of intensity I is coming out, is made incident on the polarizer. Okay. Then falls on the first polaroid. Then naturally the intensity of light coming out to the polarizer I1 will be half of I. Okay, that we all know because half is absorbed by it. Then you have another polaroid where the axis between them are inclined at 30 degree. Okay, so the intensity of light coming out through the second polarizer, which you can call it as analyzer, is the intensity of incident light, which is I1 into cos square theta. This is from law of Malus. So this is I by 2 and cos square 30 degrees root 3 by 2 whole square. So finally you have 3I by 8. Then coming to question 23, two polaroids are kept crossed transmission axis at 90 degrees to each other. Crossed means like this. The path axes are at right angles to each other. What will be the intensity of the light coming out from the second polaroid when an unpolarized light of intensity I falls on the first polaroid? Answer is 0, students. Okay. Now here you see again unpolarized light is made incident here. Unpolarized light will always have dot components and the arrow components. So if intensity is I, Here the intensity will be I by 2. Half of the amount of light is absorbed by the polarizer. Then you have another polarizer, which we'll call it as analyzer. This is Polaroid. So here angle is at right angles, 90 degree. So here angle is 90 degree. So here intensity, final intensity emerging through this will be the intensity of the light which is incident into cos square 90 degree. Cos 90 being 0, answer is 0. Then coming to second part, what will be the intensity of light coming out from the second Polaroid if a third Polaroid is kept at 45 inclination between them? So here you have additional Polaroid. Okay, here this pass axis makes 45 degree, and here again it makes a 45 degree, half of 90. So in such a case, we can solve this. Quickly I'll do this. So this side you have I intensity. This is the pass axis. When it emerges to the first Polaroid, it becomes I by 2. Then you have the second Polaroid. When it emerges from here, you have, according to law of Malus, I by 2 into cos square of 45 degrees from law of Malus. So I by 2 into I by 2. Sorry, 1 by 2, that is I by 4. And again you have another third, this thing, which angle of inclination is again 45 degree. Okay, so when it finally comes out, incident light intensity is I by 4 into once again cos square of 45 degrees. Cos square 45 degrees is how much? Half. So final answer is I by 8. So tan inverse 1.5 will be roughly about this. Similarly for the water, IP will be tan inverse 1.33, which is this. So these values, in order to know the exact values, you need to use calculators or you need to use trigonometric tables. Then coming to next question, I naught is the intensity of light existing between two cross Polaroids. Cross means their path axes are at right angles to each other, kept with their path axis perpendicular. Third Polaroid is introduced between them. What must be the angle between the axis of the first and the newly introduced Polaroid to get the maximum light intensity for the whole arrangement? So this is, you can see, I naught is the intensity of light existing between two cross Polaroids. Okay, so that means this is the first Polaroid, and here already I naught intensity is there. Then you introduce another Polaroid, let us say the second Polaroid at an angle theta. A third Polaroid, so this is the third Polaroid introduced between them. What must be the angle between axis of first and second? This is what is required. Then you have second one, which is inclined at 90 degree minus theta. So here the intensity when it emerges to the third one is I naught into cos square theta according to law of Malus, and when it emerges through this, it will be intensity of incident light into cos square of angle between the planes of transmission. So this will be I naught cos square theta into sin square theta. Okay, so which can be written as I naught by 4 into sin square 2 theta, because 2 sin theta cos theta is sin 2 theta. So in order to have maximum value, sin square 2 theta should be maximum, which implies sin 2 theta should be maximum, and that maximum value is how much? 1, when 2 theta is 90 degree or theta is 45 degree. So the angle required is 45 degree, and that maximum intensity will be I naught by 4. Okay, then probably the last question. An unpolarized light of intensity this much passes through 3 Polaroids such that the axis of the first and last Polaroids are at right angles. what is the angle between the axis of the first and middle polarized so that emerging light has an intensity of only this much. So just now we'll be using this equation, students. Okay, I naught cos square theta sin square theta, where theta we have to find. So final intensity will be I naught sin square theta cos square theta. So this is 3 watt per meter square, and incident light is having an intensity 32. Okay, you can multiply and divide by 4 to get this. So finally I can write that sin square 2 theta 4 eighths is equal to 3 by 8. Therefore sin 2 theta is root 3 by 2 root 2. Or we'll do one thing. Let us so this is 3 and this is 32 and this is sin square theta cos square theta. So if you extract the square root, we have sin theta cos theta is root 3 upon 32 can be written as 4 into 8, 16 into 2. So 4 root 60, 4 root 2. You can write this as 4 root 2. Multiply and dividing by 2, I can write sin 2 theta. If I multiply both sides by 2, we have root 3 upon 2 root 2. So I don't think you will get some fixed answer, okay? I mean, this is not standard angle. Maybe somewhere we have gone wrong. So we can stop here itself. Okay. So I hope you enjoyed this. Thank you so much for watching my channel.